Morning, everybody, and welcome to this session of Physics 101. Today is Monday, November 28th. We are the week after the Thanksgiving week. So we have quite a few things to do this week. So because we have an exam next week, we have another exam the week after. We have to prepare for these exams. We have a review this week is going to be available for you guys to prepare for midterm 3 or exam 3, I should say. Exam 3 has several components in it, so you have to be aware of that. The fact that we did a review before Thanksgiving, we did the problems in the lab discussion session. That's a discussion session focused on the problems that are, at least some of the problems that can be in an exam. You will have that part, that exam 3 part 2. And also we have the conceptual part of the exam 3, which is available for you for your review. It's available for this week. So there are 2 components for this exam, similar to exam 2. In a sense, you have 2 components there, one component being a conceptual component and the other component being problem solving session. So make sure you do both. Both are going to be available next week on Thursday, and both are going to be due next week on Friday. So by Friday, December 9th, all the exams and all of the assignments should be basically due, with the exception of one assignment that is going to be due on December 10th, namely the last lab. Although the last lab, you will be submitting it in class, but just to allow for some of you who are not going probably be able to make it on Monday, what would that be? Monday, December 5th. Some of you cannot make it for that lab so that you can submit your lab by the weekend, that weekend. So all assignments, as a matter of fact, they will be due by December 10th. So please follow the steps that they are outlined actually on Canvas. And I will follow up with more messages. One important also thing to distinguish this last 2 weeks of instruction is there is no required discussion sessions. You are still encouraged to submit discussions, but they will not be graded. So in a sense, you're not required to do them if you don't feel like or you don't have anything to share with us. But if you do, please do so. And they're not going to be graded. That's the only difference for that for this 2 weeks. And all of the previous discussion sessions have been basically posted, and you guys are supposed to do them and meet them and so on and so forth. Okay. There are videos also. There is at least one more video quiz for you guys to submit. So make sure you do that. And this last 2 chapters are important because they're actually included in exam 3. So don't skip these 2 chapters, namely chapters 24 and 25. So at least this is in terms of the overall organizations. Just to make sure that everybody is aware of the fact that we have a final for this class, and the final is comprehensive, and the final is actually the week after. So it's going to be on December, I believe, 14th, but let me make sure, okay? It's actually December 13th when it's due, okay? So that is the final exam. And hopefully you guys have, you're ready for them and you take care of all of the things to be ready for it. There is no review for the final because you're supposed to have done all of the exams before, exam 1, 2, and 3, and those are actually your reviews. So the final is comprehensive and is supposed to be based on all of the previous exams. Okay. So this is in a nutshell in terms of announcements. I hope that you guys are following all of these things and taking care of the things that needs to be done in order to pass this class well. We still have 2 chapters, though, in terms of contents that we have to cover. And we have labs also. Today we have a lab in dealing with nuclear physics, basically. And we're trying to understanding the concept of scattering, which was essential for Mr. Rutherford to trying to determine the size of the nucleus. So this is important, and we're going to do that today. And we have another lab next week, and that will be a lab where the report will be prepared in the lab itself. So you're not going to go home and prepare the lab report. Okay? So this is in a nutshell what's going on in terms of all of the content, in terms of all of the labs, in terms of all of the assignments. Okay. So there will be no more homework assignments. All of the previous homework assignments that were done and were due, that's it for the last 2 weeks. The focus is on this exams and the final. So let me share with you a screen so that I can get started. And this will be my notes. So let me start from the top. Ignore these 2 pictures for right now. We're going to get into them. But the idea here in this chapter is 24, first of all. So there are 2 components in here for this discussion, is that up to this point, we arrived at a model called Bohr's model. And just a reminder, Mr. Bohr basically assumption that the angular momentum of an electron orbiting the nucleus is given by this relationship. So this is the angular momentum, and it's just a constant divided by 2 pi, which is another constant, by the way, times this integer. So this is an integer n. Namely, n can be 1 or 2 or 3, and so on and so forth, all the integers that you can think of. In doing so, combined with classical mechanics, combined with F equals to ma, namely the force, which is electrostatic force in this case, which is the product. So there is a constant in here. This is just a constant, which is 9 times 10 to the power 9 in Newton per Coulomb squared times meter squared. So it's just a constant in here, times the product of the 2 charges. And in this case, I'm dealing with the hydrogen atom, and the hydrogen atom assumes that there is a proton of positive charge and an electron of a negative charge. Both the values of the charges in magnitude, they're equal to 1.6 times 10 to the negative 19 coulombs. So this charge, this force is an attractive force. So the nucleus is pulling on the electron and the electron is pulling on the nucleus. So that's basically how the atom is held together by this attractive force. So I'm not really bothered with the sign in here. The sign in here indicates for the electron that is being pulled inward, okay? That's all. So it's E squared because the product of the 2 charges, and the 2 charges are the same quantity, divided by the distance squared. So this force must be equal to ma, the mass of the electron times the acceleration of the electron. And the acceleration of the electron in this case is the velocity of this electron divided by the radius. And again, it's an inward acceleration. This is centripetal acceleration of the electron, v squared over r, scaled by the mass of the electron. And now you have everything. So this is F equals to ma. This is classical mechanics. This is Newton's second law. Now, he combined several ideas. This is coming from Coulomb's force, which is actually Maxwell's part of Maxwell's equations. And this is Newton's second law. So it's a combined of classical mechanics. Both of them are classical mechanics. Classical physics. Classical physics combines classical mechanics of Newton and Maxwell equations. Basically, that includes, among other things, is this Coulomb's law, the electrostatic force between charges. So that is the idea. But the assumption in here, he made an extra assumption in here that the angular momentum, and angular momentum for an electron, by the way, is just its mass, because it's treated as a point particle, times its velocity. That's all. So the mass of the electron times its velocity is given by this relationship. In doing so, he was able to come up with an expression that matched the experiment beautifully, that the energy transition between the different energy levels, first of all, it's quantized because of this n that appeared in here, an integer n. And this corresponds to the expression that is basically, first of all, this is a given number times the difference between the square of the 2 different energy levels. I'm assuming that I'm transitioning from an N1 level to an N2 level, okay? Or vice versa, actually. Yeah, that's fine. Anyway, the point in here is that in transitioning between energy levels, it's discretely proportional to the 1 over n squared, and that's fine. This is actually an expression that Mr. Balmer has already stated before, based on observations, based on experiments only, okay? For the emission or absorption spectrum for hydrogen. So the spectral lines for a spectrum of hydrogen. In other words, the theory works. It looks like Mr. Bohr's assumptions work. If you do this for the angular momentum, and if you assume that the electron still obeys classical mechanics, F equals to ma, and just replace the F in here by Maxwell's equations, basically version, so everything looks like it's fine, and you can reproduce the spectral lines for hydrogen, take the hydrogen, and you're going to find the spectral lines, their wavelengths. This is 1, 2, and 3, and so on and so forth, correspond to the wavelengths that are produced by this expression, because this is a difference in energy, and the difference in energy in here would correspond to the transition between different energy levels, and the energy levels in this case correspond to wavelengths, so the wavelengths in here will be met by these energy transitions, and everything looks good. Everything looks beautiful. There's a problem, though. Not just one, several problems. The first one is that this system is unstable. I know because he immediately recognized that this thing is not stable. So he made another assumption that the electron orbits in stable orbits without any justifications. But we know that a charged particle will emit radiation. Charged particle, when accelerated, emits radiation. So even if the electron is sitting still, going around basically a nucleus, so this is the proton, I'm sorry, and this is the electron, the fact that it's going in circles, it's accelerated, and the acceleration is that exact same value, v squared over r. Since it's an accelerated particle charged, then according to classical mechanics, Maxwell's equations, actually this electron will radiate energy, will radiate electromagnetic waves, will radiate EM waves on its own without having to transition between an energy level or another one, being excited or not excited. So this will emit energy, and if you compute it, you will find that the path actually will spiral on the nucleus until it falls onto the nucleus. So that's what classical mechanics says. And this is not observed. We don't see this a neutral atom of hydrogen, for example, emitting a radiation on its own. It has to be excited to emit radiation. And that's basically the bottom line. You have to heat it up, for example, or you have to put it in a big difference of potential, or you have to give it some light, for example, that corresponds to those transition between the energy levels for it to emit light. Otherwise, it will not emit on its own. So this is not possible. So this creates a dilemma for Mr. Bohr's model. And in order to remedy that, he artificially basically stated that let's make this orbit stable. Somehow they are stable. Okay. So this is an artificial fix. He has no justification for it. As much as he did not really have justification for the angular momentum, he just made it a postulate so that his observations will match this expression. Remember, H is a constant. H is just a constant that Mr. Planck has put together to match the theory for the radiation of the black body with the experiment. So H is just a number, 6.626 times 10 to the negative 34 joule second. So that is a constant, okay? And that matches the theory, apparently, if you just follow this analysis. But as I was saying, there is this problem. Problem 2, actually, and it's also another major problem. This does not explain the rest of the elements. Okay, in the periodic table, there are some 100 and something elements. I know a lot of them are artificial, but at least in NITRO, there are some 92 elements in the periodic table, almost 100. So if you only have a theory that explains one of them, but fails to explain everything else, that's a problem. That's not good enough. How about helium, which is the next lightest element in the periodic table? So if all you can do is just explain the hydrogen atom, mind you, not the hydrogen molecule. Okay. So hydrogen atom. Okay. How about helium? How about lithium? How about beryllium? And so on and so forth. The rest of the elements in the periodic table. Well, how about them? Well, for that, the theory actually can explain something about helium and lithium and beryllium and the rest of the element periodic table. If you strip them of all of their electrons except one, namely, if you take helium and you ionize it so that you only have one electron left, namely, there are 2 protons inside and 2 electrons, of course, 2 neutrons, I'm sorry, in the nucleus. But then you remove 1 electron and you will be left just with 1 electron. Remember, you have 2 positive charges in here and 1 electron charge, so that one of them will cancel the other, so you'll still be left with a positive. That's why we put a plus in here, okay? So in this case, the theory seems to work. Same thing with lithium. Instead of having lithium, normal lithium, which is neutral, you add to it, you remove to it 2 electrons so that you'll be left with 1 electron at the end of the day, and so on and so forth. So if you do this approach, it seems like it works for single electron atoms. Okay, other than that, or hydrogen-like atoms, if you wish, that's how they are called, then that's fine, but that's not good enough. You would want to understand, not just as a matter of fact, the atoms, but you would want to also understand the molecules. You would want to understand the solid state itself, solid itself. And this theory is not good enough for any of that, okay? There were other problems with the model itself, but basically the model at this point was successful for hydrogen. So excited by that reasoning, Mr. Bohr actually tried to generalize it to other ideas and to other elements, and he could not generalize it. So it got stuck into that hydrogen atom. So in the same time, there was another student actually by the name of de Broil. I know people complain about how do you say his name, but that's how it's spelled, okay? D-E-B-R-O-G-L-I-E. So the way it's written is de Broglie, and it's a French scientist who was actually who did not really major in physics to begin with. He started with the humanities, and he focused a little bit on physics at the end, and he made an assumption. For his PhD thesis, he was a student at that time, grad student, and so the way we say his name is actually de Broil, but that's fine. You can say it de Broglie if you want to, because a lot of people struggle with his name. So Mr. de Broil made an assumption in his thesis, and the following assumption is based actually on the observations of Einstein. When Mr. Einstein tried to explain the photoelectric effect, which he successfully did, and he won the Nobel Prize for, when he tried to explain that, Mr. Einstein made an assumption that the energy of the electron, just like as much as when the energy of the photon, the energy of the photon, and he's the one who basically came up with the word photon for the particles of life, is proportional to, again, h times f, and the momentum actually of the electron in this case, the photon, in this case, is simply equal to its energy, which is hf divided by the speed of light, okay? Remind you that f over c, or f times lambda, is still c. This is true all the time. This is true before. This is true for waves. And since a photon is a wave, actually, it's an electromagnetic wave, so it still has this relationship. So this expression then becomes h over lambda. That's it. Because F over C, that is lambda. Or, yes, C over F is lambda. And F over C is 1 over lambda because of this expression, which is true for all waves, no matter what, as long as you have the speed of the wave C and the wavelength lambda and the frequency F. So this is the frequency, this is the wavelength, and this is the speed, in this case, the speed of light. Because we're dealing with light, actually. Photons are like particles of light. So Mr. Einstein made this assumption, and it worked for him. So he turned a wave, namely the electromagnetic wave, into a particle. And he gave it a momentum, and the momentum is given by this expression, h over lambda. That h is still that same h that we have all along. The h is still the same number, 6.626 times 10 to the negative 34. This is coming from the work of Mr. Planck. So this is the same constant. It's just a number. It's not something mysterious about it. It's just a small, tiny number, 10 to the negative 34, extremely small. Divided by the wavelength, they give you the momentum. So this is an important concept in here. You have a momentum. Although photons do not have mass, they are massless. But in the case for this particular case, they behave as if they do have a mass while they're moving. So when a photon of light hits a metal, it ejects an electron because of the collision between these two particles. Because now you have an incoming momentum and you have an outgoing momentum for the electron. So this is the momentum for the electron. And there is conservation of momentum, there is conservation of now energy, and now the problem can be solved. And Mr. Einstein explained it perfectly. As long as you have a threshold of a momentum, the threshold of energy that exceeds what is known as the work function for the metal, namely an energy high enough so that it can really extract an electron. Otherwise, electrons will fly all the time whenever light hits them with low frequencies, and that's not true. So it has to exceed a certain threshold for the photoelectric effect. So that you know the photoelectric effect is what is on your ceiling or what you see on buildings nowadays for the solar, what do you call them? The solar panels. So that's basically what the photoelectric effect is. So, and some watches, some actually phones and some calculators, they use that to charge. Anyway, the point being in here is that you create charges in this case that you can store them in batteries and use them later on. So the point being in here, this is the photoelectric effect, and it makes an assumption that a wave behaves like a particle. And not only that, he gave it a name, a photon, which is a particle of light. So Mr. de Broglie, he made the argument backward in his PhD thesis, and he said, oh, how about if the electron, which is a particle, by the way, can also exhibit wave-like behavior? Namely, the electron has a mass and has a velocity, so it has momentum. The momentum is just mass times velocity, that's all. Because it's a particle. Particles have mass. And like the photon, which does not have mass, yet it ends up having a momentum in this case. So it was behaving like a particle. Now, particle like a proton, or an electron in this case, has a definite mass and has a velocity while it's moving. Then in this case, he says, okay, all I have to do is just take this expression and rewrite it as the wavelength lambda for it. So it has a wavelength, which is kind of weird to say, which is equal to this expression. This is the same expression, really. It's still valid. Mathematically speaking, if you give this expression to somebody and you tell him P is equal to H over lambda, solve for lambda, they will tell you lambda is equal to H over P. That's simple. All you have to do is multiply both sides by lambda and divide by P. So when you multiply by lambda, lambda cancels from this side. And because lambda over lambda cancel, you'll be left with an H, and in here lambda times P, but you're going to divide by P, so P cancels on this side now, and it's going to reappear in the denominator in the other expression. So mathematically speaking, these two expressions are the same, one and the same, but there is a big difference in terms of the physics. Now here, a particle like the electron that has a definite momentum, which is mass times velocity. When you take that same number, which is just a fixed number, 6.626 times 10 to the negative 34, so this is a constant, and you divide it by the momentum of the electron, here comes a wavelength. So the electron behaves as if it's a wave. That's basically the whole point of his argument. Obviously, the idea was so crazy. I mean, it was not. This is a particle. Yes, Mr. Einstein, based on the photoelectric effect, borrowed the idea from Planck for the energy quantizations for the light, and used his argument that he made before for the energy of a system, and found that energy must be proportional to the momentum times the speed of light, regardless of whether or not you have a mass or not. But especially if you don't have a mass, that's the only expression that comes in. So from that case, he argued that the photons or the light behaves as particles. He gave them a name, photons, and he was able to successfully explain the photoelectric effect. His advisor didn't know what to do with this. They were kind of puzzled. They were hesitant, especially he's coming from a background of a non-physics major. So they were kind of, are we going to accept this, or what's the argument for it, or something? So they took this whole work and they showed it, among other things, to Mr. Einstein at that time to see, does this really hold water? Is this argument sound enough? And he didn't find any problems with it. He thought that that makes sense. I mean, if light behaves as particles, why not particles behave as light? So there is a duality in here that Mr. de Broglie has brought up into the picture. And this duality is that waves behave as particles. So this is behave as particles. For that, you say that their momentum is just h over lambda. Now, de Broglie flipped this side on its head, and he said, well, particles also can behave as waves. All you have to do is just find the wavelength as being h over p, or h over mv, just to write it as classical expression in here for the momentum. Okay? Everything seems to be fine. Of course, he didn't have an experiment to support his arguments. We have to find the wavelength for the electron to do that. And sure enough, actually concurrently with his work, there was an experiment that was conducted by, what is his name again? Is it Germer or Germer? I really don't know how to say the Davison and Germer, both of them, or Germer. And they were puzzled actually by their observations, because they were doing electron beams, trying to study them. And there was an accident in the lab one day, and that accident resulted in patterns for the electrons, basically as they hit the plates, that produce patterns indicative of diffraction. So they were trying to show their observations in a conference, and one of them thought, oh, wait a minute, that's a diffraction pattern, that's waves. So here, by accident, if you wish, the experiment has shown that actually electrons do indeed behave like waves. electrons. So this is an experiment now. We're not talking about the theory or based on nonsense, basically arguments or something like that. So indeed, electrons behave as waves. The only trouble with it is if you would want to produce the diffractions that you need, or if you would want to produce the interference patterns that follow from, for example, a double slit experiment or a single slit experiment for the diffraction patterns in here, you really have to have slit openings that are of the order of a wavelength. So it helps to really have that comparison. What are we talking about? What kind of size we're talking about? So, for example, you would want to use, and now we have applications among other things for this one called the electron microscope. So let's say, for example, you shine a beam of electrons and you would want to produce the picture of a certain atom. And here is an example in the book, and I always, when I ask you guys to do the reading, to make sure you do the working it out examples, because they help you a lot trying to understand the ideas behind it, okay? Trying to understand all of these big ideas. So for the case of gold, let me try to find the number for you guys. It's from the book. I'm trying to find the page for it. All of these ideas basically are leading to a very, very important point in here, and namely the modern view of the quantum mechanics, because this is the foundation for quantum mechanics. It doesn't matter. Let me see if I can find the number in here. Okay. So a gold atom that is about 0.288 nanometer across. So you would want to take a picture of an atom that has the size of 0.288 nanometers. So we'd want the wavelength to be of that order of magnitude. So we'd want to find how fast the electron can go. So you'd want the wavelength to be of this order of magnitude for a microscope to do that, okay? So that's basically the bottom line. So if you're curious trying to find the frequency that needs to be corresponding to this one, the frequency is simply equal to, if it's light, okay, if light. So the frequency needs to be C over lambda, and the frequency then in this case, we're talking about the extremely high frequencies, okay? So this is 3 times 10 to the power 8 divided by 0.288 times 10 to the negative 9. Obviously, 3 divided by 0.28 is about 10. Okay, it's about 10. I'm not going to do the math exactly, but if you do, it's going to be a little over 10. Times 10 to the power 8 plus 9, that's 17. That's 10 to the power 18 hertz. Extremely high frequencies. This is in the X-ray range. Okay. And at that time, the X-ray technology was not developed, but now even now the X-ray technology is super energetic, and then it's very hard to contain, and it's not really something that you would want to be dealing with, especially this high frequencies. Actually, it's in the upper end of that range. So what you get to do now, you can't use light. Remember, light is between 300, visible light that is, and 700 nanometers. The shortest one is 300 nanometers. And 300 nanometers is more than 1,000 times bigger, longer than this one. So light, if you take light, for example, a regular microscope, and you try to see the atom of gold, for example, you're not going to see it. Too small for the microscope to resolve it. You can't use a regular microscope, the one that is in the chemistry lab or the biology lab, for example, and you put a gold plate underneath and you try to see the individual atoms for gold. You're not going to see that. Why? Because the wavelength is about 1,000 times longer than the size of the atom. So it's not going to resolve these atoms. Looks like a straight line for you. Okay? So you need something that can resolve those distances, basically, that has a wavelength. So if there is an atom in here, so it's going to penetrate those two, and the wavelength will be at least of that order of magnitude. So the wavelength needs to be of this number. So how fast the electrons need to be? Well, in this case, we know that the mass of the electron times the velocity of the electron is equal to the momentum, and the momentum will be h over lambda. H in this case is 6.626 times 10 to the negative 34 divided by lambda. Lambda is 0.288 times 10 to the negative 9. And the mass of the electron is 9.11 times 10 to the negative 31 times the velocity. From here, we can find the velocity to be exactly 6.626 times 10 to the negative 34 divided by all of these numbers, 0.288 times 10 to the negative 9. That is the wavelength. Divided by the mass of the electron. The mass of the electron is 9.11 times 10 to the power negative 31. We usually, when we have these big numbers, we usually deal with the powers first. And the powers 10 to the negative 31 and 10 to the negative 34. Negative 34 minus negative 31 is actually negative 3. Negative 3 minus 9, that's going to be positive 6. So the whole thing in here is going to be 10 to the power 6. Okay, so far so good. But then I have 6.626 divided by 0.28. Roughly 0.28 is about 3.3, that is. So I'm going to do the numbers roughly in here, okay? So I'm not going to do it exactly. So this is 6.26, roughly. I'm going to ignore this thing in here. Divided by 0.3. I'm just approximating this to 0.3 times 9. And the whole thing is 10 to the power 6. If you have the time, please use a calculator. And again, please use a calculator so that you can understand these things. This is part of the working it out. So when I tell you guys to go do the reading, make sure you do this number because they help you understand what's going on. 6.26 divided by 0.3 is about 22. Divided by 9, it's about 2. Okay, 2.3, 2.5, roughly. Okay, 2.5 times 10 to the power 6 meters per second. It's very important to compute the velocity. And it's very important that the velocity will be less than the speed of light. Remember, the speed of light, this is about 2.5 million meters per second. The speed of light is 300 million meters per second. So this number is still very small. It's about 100 times less than the speed of light. That's good. So when you're calculating speeds, it's very important to calculate speeds and make sure you compare them to the speed of light. Otherwise, if you find the speed that is more than the speed of light, there is something funny going on in here. It's not acceptable. It's never acceptable when the speed exceeds the speed of light. That means there is something wrong with your calculation or your theory, okay? But that's not the point. The point in here is that I can create an electron microscope and give the electrons at high speed, which is about 2.5 million meters per second. That's not big speed, by the way, for an electron. It's still a very small fraction of the speed of light. They're less than 1% the speed of light. So it's actually less than 1% the speed of light. And be able to take pictures of gold atoms, individual gold atoms. I can't do that with a normal light. Normal light will not be able to do that for me because it has to resolve those distances, those sizes, and the wavelength of a visible light. Even the shortest one, the violet that you can have, it's still it's about 1,000 times bigger than the actual atom itself. So it's not going to resolve it. That's it. It's basically like trying to take a very tiny object and trying to see it with your own eye. You can't, because it has to have, it has to be big enough, bigger than this wavelength, so that your eye can resolve them, because it uses regular light. So that's the same idea in here. So again, Davison Germer or Germer, I think Germer because he moved to the United States and became American, so we say Germer. Okay, not German way. Anyway, Davison Germer basically showed beyond the shadow of the doubt that indeed the electrons have wave properties. So particles do indeed have wave properties. So this expression now led to a new physics. And the new physics basically was governed by something called the wave function. Okay, the new physics is called quantum mechanics, actually. And quantum mechanics is based on the following concepts. First of all, a wave function describes the behavior of elementary particles. When I say elementary particles, at this point, I really mean the electron, okay? We're not in the nucleus yet, okay? And the wave function, typically, when you're reading about it, they use the Greek letter psi. So this is the Greek letter psi. This is, if you write it like this, sorry, psi, but you read it psi, okay? So it's the Greek letter psi. One thing to know about this Greek letter, this wave function, is that it's not a real function. Not real. What I mean by not real is there are, to take in math classes, you will know that numbers, they have different classifications. There are real numbers and there are complex numbers. This turned out to be a complex number, okay? So it's a little bit more complicated, if you wish, than your average stuff, okay? So it's complex. So it's not easy to draw. You can't draw it, okay? It's an abstract. It's more probably a better way of saying it's an abstract, okay? So you're asking, what in the world can we do that with? Because we can draw it, we can, even it's not real, so what are we going? We use its square. Its amplitude has meaning. The amplitude squared, or the square of the amplitude, that's the square usually of the amplitude. That's the one that has meaning, okay? Represents the probability. So it's really probabilistic probability finding the particle at the given location. The reason why you need, first of all, a wave. So the word wave now is forced upon us. We really don't, that's why it's called quantum wave mechanics sometimes, okay? So it's a wave function. So we need waves. Remember, those whole argument was based on the fact that Mr. de Broil made that assumption and later on shown that it really is the case that they behave like waves. So we have to have a wave in here. But there is a problem in here. The dispersion law that really we must obey is really kind of weird in a sense that relates the, we need to somehow come up with this expression that the momentum and the wavelength are related through this expression. In other words, the energy of these particles in here, energy E, should have some constant times the frequency. This is Planck's law that we have seen. And also it has to have a wave in here, and the wave is related to the energy through this expression. Divided by the speed of light is the number wavelength. So if you work out these numbers, okay, I'm sorry, the momentum, I need the momentum in here. So the momentum in here of the particle, which is really a particle, has to have this one. So when we work out this one, the equation itself will automatically come up with an imaginary number in it. just to meet the conditions in here. So this equation that later on appears is psi obeys Schrodinger's there are two dots on the O in here equation. I'm not going to bother writing it because it's a little bit complicated, honestly, but involves the imaginary number, it involves the time derivative of this, or the time evolution of this function, psi, which is a mathematical concept, as I say, it's an abstract function, and on the other side, it's the energy of the system, the total energy system, and that is given by the psi itself, times psi itself. So it's really a complicated equation, really, honestly, to write it, even for a calculus-based class. So it's really super complicated function, but that's the point of it. If you solve for that wave function, you take the square of the amplitude, now you can find the position of the electron, where it is. Usually, it's very hard to deal with this equation, even on an advanced course. So we're not going to deal with that, but we're going to immediately dive into something of interest to us, namely the easiest case where the particle is free, but is forced to be in a box. Take an electron, for example, and contain it in a box, okay? So free particle in a box. You take a box, okay, let's make it easy, okay, let's make it a square, okay? And you force the electron to be there, where the wave function must cancel at the outside because we are forcing it not to exist outside. So if I try to find the probability of it finding it outside, I have to square the wave function and I have to find it equal to 0. So that means the wave function is 0 at the boundaries, and that leads to something very, very, very important, and it comes naturally. And that's something that Mr. Bohr did not come for him naturally. He made to make that assumption, namely that the angular momentum is an integer multiple of h over 2 pi. In this case, if you force the electron to stay in a box, don't move outside of the box, and constrain it to be in the box so that the probability of it finding it outside is 0, then in this case, the energies for this electron are quantized. They come out naturally just because of the boundary condition. The fundamental energy level will correspond to a wave function that has two nodes at the end, an empty node in the middle. If you square it, it's going to look like this. Cancels, drops to 0 at the boundaries, and it has a peak in the middle. And the probability of finding the electron is, at least for n equals to 1 energy level, is going to be in the middle. If you take the n equals to 2 probability, which is another value for it that is acceptable as a solution, the wave function would look like this. It drops again at 0 from both ends. This is the boundary, basically, of the box I'm trying to draw in here. So the boundary will be 0, but when you square it, again, the wave function doesn't mean anything. So what I'm trying to draw in here is actually the real part. So this is the real part of the wave function. This is the real part of the wave function. Okay, a complex number has a real part and imaginary part, okay? So again, I really need to draw the square to have a meaning. So if I draw the square of this function, it looks like this. So again, it drops to 0 at the boundaries because we don't want to find the electron anywhere on the outside. So it has to be confined into the box. So it has a peak because of the fact that the square is always positive. So the probability of finding it is going to be somewhere around the 1/4 or the 3/4 location, not in the middle, not in the edges for sure, because the edges they're confined. So this will correspond to an n equals to 2 level. For the n equals to 3, the electron will have 1, 2, and 3. This looks like standing waves. So this is n equals to 3, by the way. This is like standing waves. And they are. In the standing waves, if you guys remember for the guitar, you have the strings have from both sides and you hit it. When you do, you create standing waves on it. And the standing waves will have a possibility of 2 notes and 1 anti-note as a fundamental mode, or 3 notes and 2 anti-notes as the first excited mode, and or 1, 2, 3, 4. No, 5. No, it's 4. 1, 2, 3, 4 notes, and 1, 2, 3 anti-notes, and so on and so forth. So this is how basically the standing waves work, and this is similar in a sense to the standing waves that we have in there. So this looks like it's a model for a free particle. Obviously, having an electron inside a box is not something that you can do, okay? So you're trying to understand, for example, where can I apply this? Well, an easy way to do it is for the polymers, okay? For the polymers, for example, you have a long chain, and inside the long chain, you can have free electrons that can move, but they move only along the chain itself, and they cannot exist outside on one side of the chain or the other side of the chain. If you take that and you try to find the different excitation levels for that electron inside that polymer, you will find that it matches the theory. So in other words, this is apparently it's a good model. It works, at least based on this organic chemistry example. Okay? So it seems like we're in a good track, okay? So trying to understand the atom, the problem is far more complicated, by the way. Using these ideas, using the electrostatic force in this case, trying to find the energy of the electron. Remember, Schrodinger's equation I mentioned really connects the time evolution to the energy. And when I say energy, the total energy. So I really have to take an electron around the nucleus, and I have to find its total energy first. So total energy in this case is given by the electrostatic energy, which is in this case simply is equal to the product of the 2 charges divided by the distance times that Ke, okay, that constant, plus, and this is a negative value because it's an attractive force, so it has to be a negative value, plus the kinetic energy, and this kinetic energy in this case, it's 1/2 of mv squared. So that is the total energy of the system. I have to express this one actually as 1/2 of E squared over C over M. The reason why I do that is because P is equal to mv, and I really don't have a velocity for the electron. I could have a momentum for it, okay? Because it turns out the position of the electron is probabilistic, so I really cannot find the position of the electron. That's one of the assumptions for it, one of the postulates, because of the fact that they can only do with the square of the amplitude of the function psi, the wave function, then I cannot really define a position, and it cannot really define a velocity in the sense that the velocity is just derivative of the position with respect to time. So I can't really do all of that complicated math. So I have to come up with a new math. And the new math now requires that I'm dealing with the momentum. So if we want v squared from this expression, it's p squared over m squared. And one of the m squared cancels the m. So it'll be left with an m in the denominator, and it will have 1p over p squared. So that's basically where that expression is coming from. And in here, it's a time evolution, which involves the derivative I was saying, because that's basically how the thing is. If I solve this equation for the case of the hydrogen atom, back to the hydrogen atom, yes, okay. Well, we find automatically that in order to meet the conditions that the electron stays bound to the nucleus, to the hydrogen, that they have the energy levels are given exactly with the same integer n. And then 2 new numbers appear automatically that did not appear with Mr. Bohr. The number L, which ranges in magnitude from 0, 2, 3, all the way to n minus 1. So n in here is from 0, sorry about that. 1, 2, 3, and so on and so forth, okay? L, on the other hand, can go from 0 all the way to n minus 1, okay? And another quantum number that appears called the magnetic number, which is m sub L. Okay, that depends actually if there is a system is inside a magnetic field. Okay, and this is important because there were some experiments that came actually later that could not be even explained by Bohr's model. One of them is a splitting of this spectral lines. If you take a hydrogen atom, for example, and put it in a very strong magnetic field, this split. So this individual line that was in here, one line, will split into several lines, 3 lines. Same thing in here. This line also splits. This one also splits. Obviously, I'm exaggerating the splitting, but that's inside a magnetic field. You're asking, where in the place can we see that, or where did we see that? Inside the sun. On the sun itself, there are some dark spots. And when astronomers try to understand, for example, the spectral lines for hydrogen in that case, on those dark sunspots, they notice that the lines themselves for the hydrogen are not straight lines. I mean, they are not single lines. They're actually split. And the splitting was given a name called the fine structure. And the fine structure now was a problem. They couldn't understand it with what we are right now. Bohr's model fails to explain that. So Bohr's model has more problems than what I just mentioned. Okay, the fact that it also cannot explain the fine structure. Even when it tried, namely it explained the spectral lines for hydrogen, it failed in the presence of a magnetic field. And it started with the sun, but now you can replicate the effect actually in lab, and that one, you cannot have it, for Bohr's model cannot explain it. So now here comes where that coupling between the magnetic field and the electron is. So the ML in here connects the direction of a magnetic field in this case, and you can have several values in here depending on this one. So it's always between L and L minus 1, L minus 2, all the way to 0, and L or negative L plus 1, negative L plus 2, all the way to negative L. It's a lot, isn't it, so far? That's not enough, though. There's another one. There are 4 quantum numbers that appear. 4 quantum numbers, let's count them. And the 4th one is the spin of the electron. Each electron apparently, and there is another experiment that showed that, can spin up or down, okay? So, and the values for the spin are always either plus or minus 1/2. That's probably the easiest of the quantum numbers to understand. So 4 quantum numbers appeared from this whole thing. And the 4 quantum numbers are N, L, M sub L, and then M sub S, okay? That's the quantum number. This is an integer that can range from 1 all the way to whatever you want to. This is constrained from 0 all the way to n minus 1. So you have to know n first to determine what L is. And this one needs to know L before you can find it. This one goes from negative L all the way to positive L, including the 0, by the way, okay? And this one is always either plus or minus 1/2, which is strange by itself because that was kind of a problem, okay? When I say 1/2, it's 1/2 of h bar, or h over 2 pi, okay? Usually the number itself is plus or minus 1/2. Remember, the angular momentum is always in units of h over 2 pi. And this is an angular momentum, the way that the electron spins on its own. I'm giving this model right now, this interpretation, but please do not take it literally, okay? The electron is too small to have an internal motion to be called the spin. But this is called the spin, okay, of the electron. So far, 4 numbers appear. This is the principal quantum number. quantum number, principal, PLE. Okay, the main one, if you want to. Quantum numbers. This is the orbital number, or it's called the angular momentum. Orbital number. This is actually the magnetic quantum number. In other words, if you take a hydrogen atom, for example, put in the presence, let's take a preference, the z direction, for example. What are the components of this angular momentum in that direction? You can have possible orientations. It could be pointing towards it, or not, or perpendicular to it, or away from it at different angles. That's what that magnetic quantum number is. And now the electron can have either a spin up or spin down. That's the only two possibilities. Either the electron is a right-handed electron, meaning that it's spinning in such a way that its angular momentum is pointing away according to the right hand or according to the left hand. So either you have a right-handed electron or a left-handed electron, no more, okay? You can't have it. It's basically when you take a screw, for example, the normal screws are like this, but you could have also screws that have a different, basically a screwdriver. So you could have a screw that you can tighten to position normally, okay? Or there are some screws actually that work backward, okay? For some weird engineer somewhere where they made the screw, left-handed screw, okay? And I think they do exist. There are some people who have those. So in other words, to screw it in, you have to actually blew it backward, as if it's trying to come out, but it's going in. So again, that's the behavior of the electrons. You can have a left-handed or right-handed electron, basically spin up or spin down electron, one pointing like this or one pointing down like this. So you could have the motion in this case, I'm going in the same direction, okay? But the electron is pointing up and down. So those are the quantum numbers that appeared, okay? So all of these numbers mean something. For the case of the hydrogen atom, these are the principal number n. For n equals to 1, then in this case, remember, L cannot be less, at most will be n minus 1. Since L is 1, 1 minus 1 is 0. So the only value for L is 0. And this is the way that the electron will be distributed in a spherical shape. This is called the S level. For n equals to 2, there are two possibilities. Either L is equal to 0 or L equals to 1. And remember, you cannot have L equals to 2 in this case because it's always 2 minus 1 at most. So it's 0 or 1. So in this case, you have three different ways for L equals to 1. They're all L equals to 1, by the way, but you can have an ML equals to plus 1 or 0 or negative 1. So in other words, the electron could be pointing in the x-axis with this distribution, or in the z-axis, or in the y-axis. We always take the z-axis to be 0, okay? But that's by convention, okay? That is usually the direction of the magnetic field, okay? So again, this is now the orientation. This is how the electrons are going to be distributed around the atom when they are at the n equals to 2, L equals to 1 level. When they're in n equals to 2 and L equals to 0, they look exactly like this, just like the n equals to 1. Now for n equals to 3, it includes the L equals to 0, which is this one, the L equals to 1, which is this one, but now there is a new value because 3 minus 1 is 2. So now there is an L equals to 2. And for that, you have several values for ML. You could have ML equals to plus 2 or minus 2, or L equals to positive 1 or negative 1, or ML equals to 0. And again, the ML equals to 0 is pointed around the Z direction always, okay? But the 1 and the 2 and the negative 2 and the negative 1, or positive 2 and positive negative 2 and positive 1 or negative 1, they have this distribution on the planes themselves, okay? In this case, it's the plane perpendicular to the z-axis. In this case, it's also, actually, this is the one perpendicular to the z-axis. This is perpendicular to the, anyway, the 3 axes, okay, orientations with these different distributions. The problem gets very, very complicated. I mean, even mathematically, it becomes a very complicated problem. And this helps us understand the periodic table a lot better. Now, if I take the elements, I know I'm gonna stop it probably in about 5 minutes, and then we'll continue the discussion down the road on Wednesday. Okay, so if I take only up to zinc, and zinc has an atomic number of 30. Okay, which means I have 30 electrons to put on the orbitals. I have 30 protons and so many neutrons in there to make the, depending on the isotope, okay? So if I start with hydrogen, I have only 1 electron. So that is equal to n equals to 1. And n equals to 1, L can at most be equal to 1 minus 1, which is 0. So the only place where we can put the electron is on L equals to 0. So this is the level S. By the way, this is called the P, and this is called D. And then after that comes the F and so on and so forth. This is in the spectral lines. But in here, you will see that all I need is sp_d, that's all. Even D is filled in here with 10 electrons, okay? But I can put in L equals to 0, I can still put another electron there as long as the other electron, if one of them is spin up, the other one has to be spin down. There is another principle I didn't talk about in here in detail, and that is Pauli principle. And we're going to come back next week, and we're going to talk about this one. Pauli principle, in a nutshell, principle, the other principle should be AL, not LE. Principle means it's the idea. Okay? Not the main. Anyway, sorry about that spelling thing. Anyway, the idea here is that no 2 electrons can have all the same numbers. Meaning, out of N and L and ML and MS, at least one of these numbers must be different than the other one. At least one. You could have more than one, that's fine. But at least one of them is different. So if I take the case of the helium in this case, the case of the helium, I have N equals to 1 for both electrons, because I have 2 in this case. I have L equals to 0 for both electrons. Since L is equal to 0, ML is equal to 0. ML can only be between negative L and positive L, all integers also. But since 0, I can have it between negative 0 and positive, so it's also 0. So for N, in this case, I have 1. For the case of how much is the L, it's 0. How much is the ML? It's 0. Then in this case, I can have 1 electron plus 1/2 and the other electron negative 1/2, and that is fine. So I can still have 2 electrons in there. That's fine, as long as one of them is different than the other one. Now, when I come to lithium, I have to account for a 3rd electron. Now, the 3rd electron cannot go in here because I have no room for it. Because if I try to put it in here, I have N equals to 1, L is equal to 0, and ML is equal to 0. And the MS can only be plus 1/2 or minus 1/2. So I can put only 2 electrons in there. So the 3rd electron must come to N equals to 2. For L equals to 0, and ML is equal to 0. Its spin can be up and down, doesn't matter. As long as it's one way or the other. Now, if I bring beryllium, beryllium now has 4 electrons. So the 4th electrons can come to here. I have to fill, by the way, the energy levels from the lowest up. Okay? That's why I have to start with the lowest value for N first. So I fill this level in here with N equals to 1. then L is equal to 0, ML is equal to 0, and MS can be plus 1/2 or minus 1/2. Since I can do that too, I can have only 2 electrons in there. Same thing in here. N is equal to 2 now. And M and L is equal to 0, because I have 3 possibilities for L now. L is equal to 0, or L is equal to 1, or L is equal to -1. So now I can have L is equal to 0 still, but I can put a spin up or spin down. So the 4 electrons can be fulfilled in here, in this case, by N equals to 2, L is equal to 0. ML must be 0, then I have no choice for that. And the other 2 electrons are either plus or minus 1/2, and I'm done. For the case of boron, no, I have a 5th electron. I cannot put it in any of these 2 levels, they're filled already. So I have to take the next case in here, which is L equals to 1. Because remember, L can be, for N equals to 2, L can be 0 or 1. So now I still have another room in here, L equals to 1. But if I put L equals to 1, what are the values for ML? Well, ML in this case can be 0, or positive or minus 1. That's it. So 3 values actually for ML in this case, okay? Because either 0 or 1 or -1. So in this case, I can actually fill more. Remember, for each and every one of these, I can put 2 electrons. So I can put 2 here with the spin up and half, positive or -1/2. I can still, for out of this, for the 1, I can still put spin 1/2 or -1/2. For the spin -1, for the ML -1, I can still put a -1/2 and positive 1/2. So I have a total of 6 electrons I can put in this level. And that's indeed what's going to happen. I can fill all the way to 6 electrons in here, and so on and so forth. Okay, I'm going to pick up this discussion next time when we meet on, because it's a lot right now, I think, when we meet next time. So I'm going to pick it up at around this discussion here from the quantum main numbers, and we will understand hopefully better the Pauli principle, Pauli exclusion principle, and try to have a better view of what the periodic table look like, and come up with the basically other ideas. Actually, I didn't mention them. For example, the uncertainty relationship due to Mr. Heisenberg uncertainty relationships. And also there is another concept that we're going to cover in this chapter, namely the lasers and how this all things came to be done. Thank you for your attention, and please, I will see you guys later on in the lab, and we'll have more discussions on these ideas, because we're going to do a little bit more nuclear physics actually in the lab. Thank you. Oh, I need to stop the recording first.